So now that we've spent some time actually talking about how to calculate energy, and I'll remind you that we've got sort of two major mechanical energy storage mechanisms that we can talk about. One is storing energy in the kinetic energy, which we also label as T. We can also talk about storing energy in interactions or potential energy, so long as those interactions are conservative interactions. And so now what I'd like to do, I mean, that's all interesting, but the question is, what's the utility of this? And there are a number of different types of utility for thinking about energy. One of them you've certainly seen back in ModSim, so we'll start with that. One sort of utility of thinking about energy is to use energy to do validation, which is to say that in general, if you've come up with a set of equations of motion and you know that the forces involved are conservative forces, you should actually be able to check your results by checking whether or not energy is conserved. There's a second thing that you can do with energy that's kind of handy, which is actually often energy is really useful for figuring out what the equations of motion are. And in particular, it's often easier to start with energy to figure out forces than it is to start with forces and then figure out energy. So instead of going from forces to energy, we can instead start with energy in order to figure out what the forces are. And that can often be a handy thing to do. And we'll talk more about that. This relates to this sort of idea of energy surfaces that we talked about before. So those are two of the things that we'll be talking about. I'm first going to focus on validation in this video and remind you of some things that we did in the last video and also some things we did back in ModSim. Okay, so the sort of big idea for validation is that you're finding equations of motion, right? And then you can check the equations of motion by seeing whether or not they actually obey the sort of other conservation law that's in play. So you find equations of motion by asking the question, is momentum conserved, or what's dp by dt, right? The time rate of change of linear momentum is the sum of forces, right? Time rate of change of the angular momentum is the sum of torques. So you can find the equations of motion using conservation of linear momentum and conservation of energy. And you can check the equations of motion by asking the question, is the energy conserved? So is the energy not changing in time? Or if it is changing in time, is it appropriate? Right? So for example, if you know where the losses are, does it actually look like the time rate of change of energy is appropriate for the system? Like if I keep track of the loss for friction, for example, does that loss add up to give me a total change in energy that's zero if I include the amount that is left that leaves the system through friction? And so we'll do just one example of that because we did spend some time doing that in ModSim. And in fact, I'll remind you of an example that we did in ModSim. It's the skateboarder problem. And the sort of idea of the skateboarder problem is that I have this ramp, right? The ramp has a mass, we'll say big M, and it has some moment of inertia, that's I. And we've abstracted the skateboarder to be some mass little m that's traveling along that ramp. And so it's the distance of the mass from the center of the ramp is r, and of course this angle is theta, and it's pretty clear for this system that I'm going to choose a polar coordinate system. And so if I wanted to ask the question, what's the energy in this, we now actually really have all the tools we need to figure out what that energy is. So why don't we start to do that, and then in the next video we'll look at some results. So if we start to do that, we need to think about what's the kinetic energy of the rider, what's the potential energy of the rider, what's the kinetic energy of the ramp, and what's the potential energy of the ramp. Well, the kinetic energy of the rider, of course, is 1/2 little m times v squared, and if I think about what the velocity is if I think about what the velocity is in polar coordinates, right, that's going to be r dot times r hat plus r times theta dot times theta hat. And if I take the velocity squared, that's the same thing as v dot v, right, which is in other words, r dot squared plus r squared theta dot squared. Right? So my kinetic energy for the rider is going to be 1/2 m times r dot squared plus r squared theta dot squared. Right? That's my kinetic energy for the rider. I can also think about what my potential energy is for the rider. But first I need another piece of paper. So if I think about my potential energy for the rider, well, pretty clearly this height that the rider is at will be r times the sine of theta. I'm going to assume that I'm including the gravitational interaction as part of the system, so there's energy stored in that gravitational interaction. So my potential energy for the rider is mgh, or mg r sine theta, and it'll actually be mgh, and I need to figure out where my sort of origin point is, where my zero level is. So I could define the potential energy as being 0 here. I could define that as being my origin point. I could define this as being my origin point. It's kind of up to me to decide which one I'd like for my origin point. But in general, my potential energy of the rider, the dependence at least, is going to be this mgr sine theta. If I think about the ramp, on the other hand, the kinetic energy of the ramp, well, the ramp is only rotating about this pivot, right? It's not moving, so the kinetic energy of the ramp is only going to have a rotational component. Right, so the kinetic energy of the ramp will be 1/2 I times omega squared, or 1/2 I times theta dot squared. And finally, the potential energy of the ramp, well, the potential energy of the ramp actually is not going to change. It's whatever it is. And if I assume that this is the origin point, the potential energy of the ramp will be 0. Right? So at this point, I could actually write out a complete expression for the total energy of the system. So that will be the kinetic energy of the rider plus the potential energy of the rider, which that and potential energy includes that interaction between the rider and the Earth, plus the kinetic energy of the ramp. And I don't really need to include the potential energy of the ramp because that's never going to change anyways. Okay? Now, as long as this thing is pivoting and I haven't included friction in my equations of motion, there are no losses. And since there are no losses, my expectation is that the total energy ought to be constant. So when I actually run my simulation, I would expect that although the kinetic energy of the rider will change, the potential energy of the rider will change, the kinetic energy of the ramp will change, all of those things might change, but this total energy ought to stay constant. If it doesn't, I'm going to have to ask a question, is there something that I'm not thinking of? Is there something I've done wrong with my equations of motion?